we're going to be looking at parallel lines and transversals. So parallel lines, I think you know what those things are. And a transversal, if you know what the word transverse means, anybody know that? Transverse? Traverse? It means you're crossing something. So a transversal line crosses those parallel lines. So we're going to be working with those actually mostly next class. This class, I just want to give you a very brief introduction, reintroduction of parallel lines and other kinds of lines. So I don't know if you guys have a piece of paper. You can actually do this real quick, or if you can find a little spot. On the back of this, actually, there's some blank space on the back of the notes here. And see if you can draw. We're going to do a little three-dimensional drawing here. So you're going to make two rectangles like this. See if we can make two rectangles like this. We're doing it? Okay? Yeah. All right. And once you draw your two rectangles, basically what you do is you kind of join different vertices. So, whoops, that was a very straight line. So I'm just basically drawing the different vertices, connecting corners, basically. So it turns that into that. So we're just connecting corners, and that's how you can make a nice three-dimensional cube shape.
It's a nice tutorial.
Yeah, it's kind of nice. And then I'm asking you to kind of erase the hidden. So you know how the dash lines are kind of the things that are invisible to us? So if you have an eraser, great. If you don't worry about it. But this just helps it maybe pop a little bit. So you can see that this corner is coming out to us. That corner is kind of behind us, hidden, using our X-ray vision to see what we got. And once you have that, label the vertices. J, K, L, M across the top. And P, Q, R, N across the bottom. We're also extending some lines here. We've got line LQ. We've got line JM. So just keep referring up here to try and get your drawing. And then we'll be able to kind of answer some questions about it. We got our drawings? Because we're gonna answer some questions here. So let's look at this. Will the pair of lines ever intersect in space? So I'm going to give you some pairs of lines. And so now this is 3D, right? Three-dimensional space. So will lines JM and LQ, JM, think about where that is, and LQ, will they ever intersect in space?
No.
No? How come?
Because they're skewed.
Yeah, one's in front and one's behind, right? And they're not going to ever touch. So that one's a no. How about JK and NR? Now think about that. If you were to extend them, are they ever going to hit each other, ever? So again, this is very abstract thinking. So, Keely, would you say? No. You kind of have to extend that in space there. How about QR, who's up this guy, and MR? QR and MR, are they ever going to intersect? Amanda, what do you think?
They intersect in the picture.
Yeah, so that's a yes. All right, it looks like they hit right over there. How about LM? There we go. MR. LM. Yeah. Yes. Okay, let's see what else we got here. KL and NQ. Well, NQ, right? You have to kind of imagine what that one is. Right? And so any 2 points can determine a line. So there's NQ and then KL. What do you think? They say pious, I'm shaking my head. No? Do you think a degree? No?
I agree.
Yeah? I think they're not. So there's actually implied lines maybe we don't see necessarily. How about the pair of lines lying in a plane? So let's check it out. JK, there we go, and QR. Do they lie or can they lie in one plane? Yeah. So this one, in fact, I don't see that plane. Well, no, I don't either. But if you look at those two lines, could you draw a plane that contains both of them? So that's a yes. And I believe we have a postulate, right? Two lines can be in a determinate plane here. QR and MR. Can they make a plane? Well, yeah, you can actually see that plane in the picture, so I think that one does. And what about now JM? This one and LR. So LR is one that we're not given. we fit a plane on that? What do you say, Amy? Not really? It's a yes or a no? Does it? Can we? So, like, you have to draw this, so one's out here, and one's kind of going sideways. Can you fit a flat piece of paper on them? If I cut it out, I want to cut it out, right? So I got J, N, and L, R. Yes or no?
No.
No? You say yes? Well, it's a camera.
Yes, but it's four pins, each in a different dimension.
Well, it's like this one goes straight up and down. So think about the planes that you can fit around here. And this one is kind of sideways. Think about the planes that can fit in that line. They don't agree. It's LR. So it's kind of like a diagonal going through here. Yeah, that's a no. And then what about JL? So again, another one, we kind of have to imagine that line. And NQ. This one. What do you think? Yeah, I think this one I think is a yes. Because, let's see, this one's this way, and that one's that way. So they are lines that it looks like I could fit a piece of paper on top of them. So two diagonals.
Oh, I thought we were.
We're looking at JL and NQ.
Okay, I understand now.
What?
I thought.
This is the plane.
It's right, kind of paper, can you lay a piece of paper on it? It's kind of how you look at it. So let's see, do pairs of lines that intersect in space also lie in the same plane? Yeah, what do you think?
So planes can't be curved, right?
No, not in Euclidean geometry, no. Not what we're doing. Planes are flat by definition in Euclidean geometry.
Then what is a curve equivalent of a plane?
We'll talk about that like a little bit after this lesson. Let me get through this part. It's not, all right, so answer this question. Do pairs of lines that intersect in space also, so think about pairs of lines intersecting. So here's some lines that intersect, right? Can you make a plane? What do you think? If they intersect, can you have a plane? We can't always make a plane with intersecting lines, is that what you're saying? When you think of a case where lines are intersecting and I can't make a plane around them. So if I'm looking at intersecting lines, what's the definition of a plane? Three non-collinear points? So if you have intersecting lines, I know I've got collinear, but if they're intersecting, doesn't at least one of them have to be non-collinear? So I think this is yes, because we can find three non-collinear points. So the question is if they don't intersect in space. So what if we have some lines that didn't, right? So let's look at JM and LQ, right? Can I fit a plane on lines that don't intersect? No. That's our no. So if they intersect, yes, you can make a plane. If they don't, no. Well, parallel lines? Oh, okay. So if I have M, R, and LQ, they don't intersect, but I could put a piece of paper. So we're finding what? That if they intersect or are parallel, then I can have a plane. But if they don't intersect and are not parallel, then we don't. Which is what we wanted to kind of conclude from that little picture. Lines that intersect are coplanar, always. If they don't intersect, two things can happen. They're parallel, in which case they are coplanar, because parallel lines are coplanar, therefore we have a plane. And if you have parallel lines in a plane, this little marker here, this is how you show on a drawing that you have parallel lines. So that's all that that's telling us. And we use, again, we've used this already. This is our notation, line M parallel to line M. So that's one thing that can happen. The other thing that can happen is you have skew lines. So let me finish this and I'll take your question. A skew lines are lines that are not coplanar. So that was like the case over here where you have one going this way and one going the other way. They are not coplanar lines. So there are a couple questions? I saw the hands up. Yeah, question?
Yeah, is that parallel symbol is also the symbol in there's also like a little operator in a lot of coding languages that means or, like in comparisons, like
This uses
if
or?
this equals this or that equals that.
Okay.
and do this.
So we have to keep straight our notation then, right? Sometimes in different situations, they'll mean different things. When we're talking in geometry, we see this, we're talking about parallel. Okay, so let's see. Let's look at this figure here. And this one we have on your notes. In the figure, name some lines that intersect. Lines that intersect. So, okay. Name some lines that intersect. We're looking. Two people see. Look at everybody else. Look at the picture. Do you see two lines that intersect? Allie, do you see two lines that intersect? Huh? K and N, right? Lines K and N. This one and this one. We're looking for lines that are parallel. Lines that are parallel, remember?
M and N.
Yeah. And how do I know that they are parallel lines? How do you
There's
know?
no markers on them.
They have their little parallel markers. So when we looked at, what can you assume, what can't you assume? If these parallel markers were not there, we could not assume parallel, but now we're being told that they are. How about lines that are skew? They do not intersect in space. Lines that are skew. Amy? K and M are skew lines. One's up here, one's down there, not unique. And here are planes that are parallel. Parallel planes. Yeah, which ones?
T, U.
Planes T and U. And it's a little tricky how I know that they are parallel, and that is something we're going to be learning next class. These little congruent angles are my giveaway, that these are parallel planes, and it is something we're going to discuss further next class why that's true. Joseph? Skew are lines in space that do not intersect and are not parallel. The picture M going forever and K going forever. Are they ever going to hit? It's kind of like you took parallel lines and you bent one in space, because now I'm not just two-dimensional anymore. This one is up front and this one is behind it.
Oh, behind it.
Yeah,
Oh.
it's like a very difficult abstract kind of visualization here. This one's up front, see it's running along this edge, and this one's running towards the back.
Oh.
Yeah, they're hard to see.
Oh.
All right, so looking a little bit more in parallel and skew lines, think of each segment of the figure as part of a line. So I'm going to talk about lines, even though they look like segments. So can we find any lines, line or lines, parallel to line CD and containing point A? Joseph? BA? Right, parallel, parallel. They're giving me a little right angle marker, so I know I've got a nice right through here. And they find any lines skew to CD at containing point A. Lines that are not parallel but will not intersect. Yeah, Julie? AF? GF. Except I have to contain A. The only, my little restriction here. Yeah, that's okay. GF, I think is right. Yeah, GF's right, it just doesn't contain A. Yeah? GA? Oh, yeah, that works. Are there any others? Yeah? AH is another one, we have two in here, that I can see. So this one and that one are skewed, they're not parallel, they won't intersect. Lines perpendicular to CD and containing A. Perpendicular to this, containing point A. See? What do you think? No, Joseph? Right? Perpendicular, I see my right angle marker, so I know this line will be perpendicular to that one, and it does contain point A. And I'm looking for planes, parallel to plane, EFG. So EFG looks like the bottom of this cube, and it contains point A. Plane parallel containing point A. You answered every single question. Let's see, who else can answer one? Yeah, Amy? G, A, C, whoa. And I want to be, I want to be parallel to this guy. D, A, C, okay, that will go with you. D, A, C, the top lid, right? The bottom lid and the top is under this guy. What?
It's not a line.
It's not a line, oh, it's not a line. Plane, D, A, C, yes. Which one? What about it? To what? A, F, you to that one? Oh, okay, I think it is.
Oh, and
And A.
A, F, so we have more than A, E?
Any point on the bottom plus A.
Any point on the bottom plus A. A, F, A, E, A, G, A, H. Yeah, I guess they are. I guess they are, good. Well, that shows we get this.
AI.
What? So you're saying anything on this plane to A will be, okay, awesome. Let's see. If two lines are in the same plane, then they are either parallel or intersect at a point. So is that true? If two lines are in the same plane, then they're either parallel or they intersect. That's on the same piece of paper. Right? Through a point, not on a line. Okay, so you've got a point, and it's not on a line.
What?
Okay, so through a point, not on a line, how many lines can I draw through this? Infinite, right? I can draw all kinds of lines. How many of them are going to be parallel to this line? How many? Okay. So the parallel postulate. Okay, if there is a line and a point not on a line, then they're exactly one line through the point, parallel to the given line. And that looks kind of obvious. Now, but this version of the parallel postulate comes from Euclid's version. So Euclid's fifth postulate was the parallel postulate. Here's what it said. I think it's always interesting to look what Euclid actually said. He said, if a straight line crossing two straight lines, so here's a straight line crossing two other straight lines, makes the interior angles on the same side. Whoa. Interior angles mean the inside angles that are on the same side of this line. If it makes them less than two right angles, the two straight lines, if extended indefinitely, meet on that side on which are the angles less than the two right angles. Got that? Now, which version of the postulate do we like better? Euclid's? Or if there's a line and a point not on the line, then there's exactly one line through the point parallel to that.
Who's got sent to jail for that one?
What? No, I mean, this was, if you look at this logically, it's like, whoa. You kind of understand it, right? Ish?
Yeah.
So this is how Euclid wrote thousands of years ago. So this very smart mathematician named Plato, a Scottish mathematician, said, let me see if I can come up with something equivalent that isn't so hard to understand. So he went and he said, well, this is another way to say kind of the equivalent thing as Euclid's fifth postulate. Joseph?
Oh yeah, earlier we had the like infinite.
For what?
There exists only like your point on line.
Oh, no. How many points are parallel? How many lines can you make?
Not the parallel line. I mean, like there's just
Oh yeah, there are infinite numbers, yes. Infinite, yes. The answer to that question is infinite. The answer to this one is one. Right? So there's an infinite number of lines, but only one will be parallel, which leads to our parallel postulate, which Euclid actually suffered through this. He really didn't want it to be a postulate, but he couldn't figure out how to prove it. Question?
So for Euclid, if the interior angle is 190 degrees and on the parallel?
Yeah, I think that's what we're getting at. Now, what if they're bigger than 90? Well, what happens on this side? You get two angles that are less than 90, you get back to where you were. So it's kind of an interesting way of putting things. This is how this guy thought. I mean, it's kind of an amazing thing. So, yeah, but it was like, what? You know, it's a little hard to understand. Yes. What? That's the name of a Scottish mathematician. He's the one that said, you know what, this is a better way of saying this, at least for our purposes to understand what's going on. So thank him. right?
At
Otherwise,
least
this
it's
would
not
be
like-
what you'd be memorizing.
Ancient Greek.
In ancient Greek, yes, that's what we should be doing. And then the last thing is the perpendicular postulate. This one caused you to put a lot less Greek. He was fine with this one. So if there is a line and a point not on a line, then there is exactly one line, or one and only one line, through the point perpendicular. I mean, this is the same kind of thing, right? The problem he had with the parallel postulate was he wasn't convinced that that was always true. And if you're playing curves, it's not always true. You know, it gets complicated. Yeah.
Parallel.
Is there something wrong on the paper?
It says perpendicular to parallel.
Oh, okay, so cross that out, it should say this. Yeah, he says there's a typo on the perpendicular postulate there. Alrighty, and that's where, what?
It's for the same thing, or
Yeah, so it should say this.
Well, maybe perpendicular is the typo, and they just want us to really know the
has
parallel
the same
postulate.
postulate, so then